So what I'm going to do is I'm going to tell you a little bit about stuff I have in mind. So again, this is not about physics, okay? Uh, so you can be totally cool with whatever it is, and you can certainly do physics. So you can see my screen. I hope I will not go to the videos. I'll try to keep it under control. Okay. So this is a paper, as you can tell, and it's from a good journal. It's from a journal called Neuron, and dating back to November of 2015. So it's fairly recent, actually. And the point of the paper is to talk about the psychology and the neuroscience of curiosity. Animals are curious. We are animals. We are curious, right? But curiosity is something that's intrinsic to our survival. So just to give you a bit of a read, curiosity is a basic element of our cognition, yet its biological function, mechanisms, and neural underpinning remain poorly understood. It is nonetheless a motivator for learning, influential in decision making, and crucial, get this, for healthy development. So you got to be curious. One factor limiting our understanding of it is the lack of a widely agreed upon delineation of what is and what is not curiosity. So now we are getting into shop talk. And the idea of the shop talk here is we don't really know what curiosity is or how to define it, which is fine, which is a great opportunity to learn more about curiosity, right? So to carry on with this point a little bit, uh, six surprising benefits of curiosity is an article by somebody who used to be a grad student at the time at Berkeley, Emily Campbell. And it says, hang on, I can't manage this stupid thing here. For children and adults alike, curiosity has been linked with psychological, emotional, social, and even health benefits. And then there is a really fantastic and well-known article uh, in this journal, Motivation and Emotion, published in 2007, that has to do with curiosity and pathways to well-being and meaning in life. We should take a look at some of these papers. I really enjoyed going over some of them, and I've given the links and I'll post it so you can take a look at them. Now coming down to something more sciencey, many of you may have heard about the Institute for Advanced Study in Princeton, which is a premier blue sky institute. Einstein was there for a significant part of his life. So this was founded by a gentleman who was a medical doctor by and large, Abraham Flexner. And Flexner wrote something quite interesting. He said, "Is it not a curious fact that in a world steeped in irrational hatreds, which threaten civilization itself, men and women, old and young, detach themselves wholly or partly from the angry current of daily life to devote themselves to the cultivation of beauty, the extension of knowledge, to the cure of disease, to the amelioration of suffering, just as though fanatics were not simultaneously engaged in spreading pain, ugliness, and suffering." Very powerful words in an essay, and you can actually find this essay, and if you're interested, I'll be happy to send you the PDF. The title of the essay is also quite intriguing. It's called Usefulness of Useless Knowledge. So, with all due respect to Abraham Flexner, the point is that curiosity actually plays an immeasurably important role in our lives. But I'll add to that something else, which I personally find important, and that's the issue of taste. And this issue was brought up by Xian Yang, who's a physicist. Yang is going to be 99 this year. He won the Nobel Prize in his 30s. He has been a major force in physics. And he writes here, and this was written on his 60th birthday celebrations: "In every field of creative activity, it is one's taste, together with ability, temperament, and opportunity, that determines one's style and through it, one's contribution. That taste and style have so much to do with one's contribution in physics may sound strange at first, since physics is supposed to deal objectively with the physical universe. But the physical universe is structure, and one's perceptions of this structure, one's partiality uh, to some of its characteristics and aversion to others are precisely the elements that make up one's taste. Thus, it is not surprising that taste and style are so important in scientific research as they are in literature, art, and music. So let's just get a sense of where we are. 1977 was the year when the Voyagers were launched, Voyager 1 and Voyager 2. I was turning 17 that year. And Voyager 1 and Voyager 2 right now is outside the heliosphere, which is the region surrounding the sun, our one and only star nearby that sustains us, where you can still feel the solar plasma, okay? Meaning that charged particles from the sun. But it's not about sun's gravity. Sun's gravity extends far, far out. So this is just the plasma sphere. And Voyager 1 and Voyager 2 are past this, and they are in interstellar space right now. So why am I telling you this? I'm telling you this because it's very interesting to see the world from the viewpoint of Voyager. And one of the things, just to point out, just as I said, so if this is the solar system here, you have the Kuiper belt around it. So Voyager is past the Kuiper belt. And then you have this enormous Oort cloud, which is the area where the gravity of our sun is still felt. And this area is enormous. So Voyager 1 and Voyager 2 won't be out of Oort cloud for another 10,000 or so years. So it'll be a while. We won't be around. But that's not the point. The point is that Voyager 1 and Voyager 2 can give us a perspective, and the perspective is this. So this is Carl Sagan's pale blue dot. Okay, that's Earth. And that's Earth viewed from roughly the position that is shown in the figure on the right, where it says Voyager 1. And this was taken a long time ago now, more than 31 years ago. That's how Earth looked like at the time. So everything we know, everything we do, all of our history is actually in that blue dot, right? So that's quite amazing. So I kind of wanted to give you this perspective before I move on to how we got here. We got here because of the Big Bang. How do we know about the Big Bang? Well, curiosity again, right? I mean, if you think about it, the fact that we have been around, this universe has been around for about 13.6 billion years, goes down to how heavy elements decay. And the age of the universe was estimated first by Willie Fowler and Fred Hoyle. And you can see one of their early papers from 1960 in Annals of Physics called Nuclear Cosmochronology. And if you go down and read the abstract, the last paragraph of the abstract basically gives an estimated age of the universe, which is quite different from what we know of today, but it's not outside the ballpark. So refinements happen, and we know it's about 13.6, 13.7 billion years, as you can see in this famous NASA picture, schematic on the right bottom. And here you see, you guys are physics students, so I don't have to explain the baby picture of the universe to you, but that's how the universe looked like, we know, when radiation and matter decoupled, which is beyond mind-boggling, that curiosity can get you there. But make no mistake that taking this picture required drawing from many things, required drawing from optics, required drawing from the science of lenses, required enormous amount of data processing, and you can just artificial intelligence. And you can go on and on and on. So even though it's a physics picture, uh, by every measure, it's a picture which has involved many different ways of looking at things. Now we are back to the pale blue dot. And in the pale blue dot, we know we have seasons, right? I wish I could show you this movie, but it'll take time, so I'm going to skip it. David Hockney is one of the very famous contemporary artists. And he lives in San Francisco. He's a British artist. And Hockney is very famous for not only his paintings, but also for photography. And if you look at this link, which I won't open it, uh, it's from one of Hockney's exhibitions, where he has taken the picture of a street with trees around in 4 different seasons and given you a window to look at how nature changes in these 4 different seasons. And it's partly because of that we are around, by the way. Had there not been seasons, had Earth not been in the Goldilocks zone, had Earth not been tilted to begin with, we wouldn't have had those seasons. So it's that tilt of the Earth that gives us the seasons, as you can see. So everything that I've told you has a great deal of chance, has a great deal of accident, has a great deal of things coming together to you know to understand what we are and where we are and why we are here and all those things. So let me now turn to something else, which is all the hoopla that we hear about climate change and global warming and what have you. So this is an interesting graph, and the graph on the left, figure 2A, gives you the concentration of O18, oxygen 18. And when O18 is high, it means it's very cold. When O18 is low, it means it's warmed up. So as you can see, from 60 million years to about 35 million years ago, Earth was very, very cold. So this is post-dinosaur era. And then there was a warm period, somewhat warm period. Then the Earth became cold again. And then when the Earth warmed up again, around 3 million years ago, the African hominids showed up. And that, of course, predated Homo sapiens sapiens, which is what we are. Uh, and we have been around during this period. So we have been extremely fortunate, actually, if you think about it, to live in an Earth which has been more habitable. We have not been bombarded with a major ice age that would have surely uh, destroyed civilization as we know it. But you see what happens. The fluctuations have gone awry for a while. It's not all that recent. We're already talking 0.5 million years when fluctuations have gone off to the crazy end. And if you look at the carbon dioxide concentration now, that's figure 1B. And here you begin to see how carbon dioxide has really shot off the scale in the recent years. And this, of course, is a big concern as to why there is such a large CO2 rise, how much of it is man-made, how much of it is not man-made. This particular picture I've taken from Professor George Philander's article. George is a friend of mine. If you have heard about the phrase La Nina, that goes with El Nino, it was George who coined that. He's one of the world's leading oceanographers and climate scientists. And he's retired out of Princeton. He's an emeritus at Princeton. So I want you to read the last part of this paragraph. To overcome the impression that the graph is complex, assume for the moment that figure 2A shows the temperature of a patient admitted to a hospital with a high fever 60 hours ago. That's got to do with the 60 million years. Medication reduced his fever, but then around 3 hours ago, he started having convulsions that gradually grew in amplitude. About 20 minutes ago, The doctor started monitoring blood pressure as well. The red graph in figure 2b, and when it went sky high a few minutes ago, the patient was rushed to the emergency room. So this is where our planet currently is at. We are at the emergency room, but we don't really understand a great deal about why. So let me just tell you a little bit about that. You see, I've been dancing around physics. I haven't talked about physics yet. Without getting into this, let's just look at the picture because you guys are physicists. You guys can look at plots and understand them. There are 4 bars out here in the fractional response. And you can see water vapor and cloud. And you can also see CO2 and other. And it turns out that we don't really understand at all how CO2 and some of the other uh, gases that are being emitted, um, how all of these play a role with cloud and water vapor to build up the cloud layers, which are primarily responsible for the most important part of the warming process because it traps and makes the Earth atmosphere into a heat bath, which can get hotter and hotter and hotter because radiation is coming in, but not enough is going out because of the cloud layer. So clearly, water vapor is very important in cloud formation. How clouds form, by the way, we don't know. Okay, this is a totally uncharted area of science. We don't know much about how clouds form. Uh, Water vapor plays a huge role, we know. Once clouds form, they play a huge role, we know. What is the role of carbon dioxide and many of these gases in cloud formation itself? We know it plays a big role. How big, we don't know. That's very much out. Uh, the jury is very much out on that. So this is an important point that I wanted to bring up today because we want to look at science and we want to look at basic questions about science and why it's important for us. Why do we do science anyway? Who told us that science is the answer to everything? Uh, we assumed it. Is there a basis for that assumption? You better be sure you're going to spend your life doing science somehow. Reshaping the theory of cloud formation. One of the important names in this work is John Seinfeld, who is the second author from Caltech. And Seinfeld is one of the leading figures in both physics and chemistry of cloud formation. And you can look him up. Uh, this is a paper from Science. And all it tells you, this 2001 paper, is that our understanding of cloud formation is mostly experimental, and there is really very little theoretical foundation. Now, you would probably ask me, if I were you, I'd probably ask my lecturer, how can we predict what's going on 7 days hence? Because you know that when you turn on the TV to listen to the weatherman or weatherwoman, you hear that, right? Well, that's because we do linear extrapolation of the data. So we have data for today, and we do linear extrapolation of the data based upon history that we know. And from that, we can tell what's going to happen tomorrow and maybe 7 days hence and maybe 2 weeks hence, becoming progressively more inaccurate. And this is why, by the way, the European and American models are not the same because the matrix involved is not the same. This is the matrix, Pi plus 1. The array for the immediate future depends upon the array right now, which is Vi, and the matrix involved, which is this matrix A. This is as simple as linear algebra can get, which is what we use. But right now, because of COVID, we are in bad shape. You know why? Because planes haven't been flying. Every time a plane takes off, it collects data for us. Every aircraft. So we don't have 50 to 75% of the aircrafts in service. We don't have good data. Our weather prediction or climate prediction has gone for a toss. Things are pretty crazy. This tells you the reason why theoretical physics is needed. We need to understand theory. Data is not enough. You need to be able to solve the equations and figure out if the equations should be improved. Now, what if you knew all the equations? What happens then? Who cares, right? You ultimately have to answer this question to yourself, if not to anybody else, as to why am I going to spend 15 years of my life, 20 years of my life struggling with physics and not getting very far and being told by everybody that I'm an idiot. Why do I have to put up with this nonsense? Why can't I go to Wall Street and make a few $1,000,000, drive a few Teslas and have a nice mansion and have a fun life, and why not? By the way, I ask this question to me all the time, uh, and I can't tell you I have a good answer, but I can only tell you my own experience. And my own experience is I do believe that we have a moral responsibility to leave the world a better place. Because if you think about the history that I just told you about, and our curiosity, our children and our grandchildren have just as much rights as we do to enjoy the planet, and to enjoy the society, right? So we have a moral responsibility, if not anything else. And if you look at all the subjects that we have, you begin to see how bad the universities have been in putting things together, right? So on the top left, I have stuff that you and I will probably relate with more often. Math, which is a language, no more, no less. And then there is science. And within science, physics is very basic. So I put it in red. That's what we all like to look at. Chemistry, not all that different. My daughter is a chemist. She thinks exactly the same way as I do. Biology, and we don't hear much about earth and planetary sciences, but that's terribly important. And we hardly hear about atmospheric sciences. Most universities don't even have an atmospheric science department or a program. So this is how bad we are in the universities. Uh, we don't talk about humanities and social sciences at all most of the time. You will go through entire grad school without really connecting with these areas, without economics, without psychology, without languages, without political science and history. Just to give you a sense of how much of a problem this is, everything that we think about when it comes to the future is somehow or the other related to history. History is that A matrix that I talked about. So if you don't know history, you are going blind forward. Okay, uh, but we don't know history. Do we know the history of physics? Hell no, absolutely not. Our knowledge of history of physics is not only very poor. What I would even claim is that there are very few departments in the United States that actually pursue history of physics solely. UPenn used to have a department. Harvard used to have a department, and there is another department I've heard of. I can't think of. There are two or three departments of history of physics right now. However, there is a gentleman by the name of Peter Turchin, who is actually more a mathematician than anything else. And Peter Turchin works on mathematical history. And he's a professor at University of Connecticut. And he analyzes historical events through a mathematical lens as a way of thinking about that A matrix that I told you about. And of course, we won't be anywhere doing all these subjects if we didn't have engineering and if we couldn't manage what we are doing, right? So if you can't run a company, what can you do, right? Because this is the way things work. In the universities, you and I think, or you and I do some experiment, we make a model, or we come up with a way to think about something, and we can think of a clever idea of an application perhaps. But universities can't do any more, okay? Then you got to scale it up and take it to some kind of a company. Uh, it's a company that uniquely takes that knowledge product and makes it into a product for society. And once it sells to society, that's when we make the money, right? And without money, without the economics, nothing can be sustained. So, so we need engineering for that, and we also need management because we have people involved. You cannot poo-poo any of these. Furthermore, nobody likes a society where we are the kings, because if we are the kings, What do the rest of the people do? And how is that even close to a balanced society, right? Think about it. We in America um, are we're the richest country in the world, and we are rich because of what? Trade, right? Because we can trade. Everybody trades in America. Um, if we are only trading with 20 countries out of 180 or so countries, does that sound sustainable? No, it doesn't. So going down in time, much of Africa we don't trade with because much of Africa is too poor to trade with us. That's where the population is. That's where the development is going to happen in the next 50 years. Okay. So it is even in our selfish best interest to do development in Africa because those countries are going to be our trading partners. They are going to be our labor force. All right. This is development, which, by the way, is what I'm doing for the past 1 year at USAID. That's why I'm not on campus. I'm at United States Agency for International Development as a Jefferson Science Fellow of the National Academy of Sciences. The other very important thing is we got to educate. Right now, if you think about education, education is only designed for those of us who live in the urban world. Education is not designed for people who live in villages. Half the world's people live in villages today. So, and we don't even have the capacity to educate them. All right. So here are some problems that you can solve while you're at the university. And they all have physics in them if you're looking for it. Of course, these are just my suggestions. You don't have to do them. Waste recycling and soil management. Does that sound fun? Uh, Plastics recycling. Does that sound fun? Do you know that we are drowning in plastics? I'm sure you know, right? But what are we doing about it? Removing carbon pollution from air should be from air. Uh, it can be done. Are we doing it? No. Do we know the science to do it well? No. Hell no. I already told you about understanding the role of water vapor and cloud formation. Desalination. We are running out of water. Great Lakes. That's all we got, right? A few other lakes, and that's it. That's your freshwater supply. The ice and the snow are melting away. They're becoming salty. So our source of water into the future is desalination. Desalination technologies are in nascent stage, man. Think about it. We are still using uh, solar panels to get solar energy out. This is great. By the way, I have solar panels on my roof. I have 22 of them, and they're very, very efficient for me. But have you inquired into how efficient they typically are? Talking 30, 40% for the best of the best. Most of the ones I got Kyocera panels, they're about 5, 6 years old. I think their efficiencies of the order of 25 to 30% on a good day. But they're good. Even on a snow-covered day, it gives me a decent amount of solar energy. Uh, but we don't use wind energy because wind energy we use with turbines. But I can't put a wind panel on my roof. It's not there. Can one do it? Of course, one can do it. I can tell you how, but it can be done. It has to be done. Can we take vibration energy? So much vibration going on. You take a train ride, you generate a lot of vibration and noise, right? You stand in a station, collect that energy. Enormous amounts of energy that you can get. Wave energy. Wave energy is gravitational energy, right? Water is heavy, rises and falls. If you just take wave energy alone, we can meet the world's energy demands uh, instantly. So the fact is that there are enormous problems to be solved, and don't lose track of it. And I'll give you a simple problem. So a sample physics problem, and these are the things that drive and motivate me. A sample physics problem, you can also think of it as a fluid dynamics problem, as an atmospheric physics problem. How do small particulates get to move in air at various altitudes? Let's take a small particle, a few microns. How does it move in air? Do we know? No, we don't know. But if you look at this part of India, this is like North, North India, Northeast India, Northwest India, Pakistan, and China, uh, this dark brown area, that's all because of particulate pollution. And as a result, there's been tremendous warming in these areas. This is the Athabasca Glacier in British Columbia. I don't know if any of you have been there. I've been there. Um, Athabasca Glacier is a beautiful place. You can walk on this glacier. And if you look at it, you see how dark it is over here. And that's primarily because uh, of particulate pollution. So this is dust from Vancouver, dust from Calgary, dust from Edmonton, dust from the industry, dust from the agricultural fields that's there. That's it. Not to mention the atmospheric dust, even some volcanic dust that may be coming around from time to time because of atmospheric motion. This picture on the top right is Sahara dust flowing from Africa to the Americas and the Caribbeans. You're talking 770 million tons of dust per year that move from North Africa to the Americas. You go to Florida, you can actually encounter Sahara dust. You go to Georgia, you go to Texas, it's there too. 2.5 microns. Just see them flying from space. How cool is that? And by the way, hurricanes form here. What does this dust do to the hurricanes? You wonder, right? I don't know the answer. I'm just asking a question. What does the science depend upon? Newton's laws. We have known this since 1680s. Can't solve it. Do we need to solve it? That alone is a big question. I don't think so. But, you know, so somewhere something incredible is waiting to be known. I love this quote. This quote is from Sharon Begley, who was a science journalist. She was roughly my contemporary, a few years older than me. And Sharon Begley just passed away a few weeks ago. Uh, but this statement of hers, somewhere something incredible is waiting to be known, uh, I find very inspiring. There are two special friends I thank for everything I've told you so far. And now I'll tell you about something that I do, I've been up to lately. And this is the reason why it's so short, because I cannot possibly explain to you why I'm doing these things right now. But I'll tell you a little bit because we have a few minutes. So, much of dynamics is solving equations of motion. Equations of motion come under the banner of what we call Liouville equation. Basically, A dot is L times A. L is the Liouville operator. That's what dynamics uh, boils down to. Newton's laws are encompassed there. Heisenberg equation of motion is encompassed there. Dirac equation is encompassed there. But these are by and large discrete equations, okay, with space and time, space in particular, taken with discreteness. But when you make continuum equations, there's a possibility that some of these equations may be integrable, especially if they're nonlinear. Nonlinear meaning what? Nonlinear in forces typically. They have nonlinear terms uh, as opposed to linear terms like harmonic motion. So nonlinear equations, continuum nonlinear equations, if they're integrable, it turns out they have specific characteristics. For example, uh, many nonlinear equations admit what we call solitons. What are solitons? They're just energy bundles that move around without dispersion. So in nonlinear equations, integrable nonlinear equations, the solitons don't interact very much. So that's very boring actually. But if you make it non-integrable, if you take into account, if you take discreteness into account, most times they become really crazy interesting. And the solitary waves, I no longer call them solitons for reasons I won't explain now. They actually interact. So you go from nonlinear dynamics to what is statistical mechanics. They actually drive the system to statistical mechanics. So my work in the last 18 or so years have really focused on the connection between non-integrable nonlinear dynamical systems and statistical physics, which is where I started my journey when I was like you guys. Granular materials are what I call Hertz systems. Materials made of stainless steel balls, materials made of sand grains, materials made of, you know, glass beads and all that. Under these nonlinear, integrable nonlinear systems come Hertz systems, granular systems, that is. Comes Fermi-Pascal systems, which were introduced by Fermi in 1954, and forms the basis of modern nonlinear dynamics. We have been very active in this field for the past 26, 27 years now. And we have made some seminal discoveries, I should say. All of them published, some of them still in the pipeline. This quasi-equilibrium is a state that I introduced in 2004. It's a pre-equilibrium state, but with very special properties that are unique to strongly nonlinear systems. How solitary waves interact is our work. And there has been singular contributions made by my group over time on this problem. Currently, we are working on rogue fluctuations, which seem to be characteristic of strongly nonlinear systems. What are rogue fluctuations? Just large fluctuations. Just weird large fluctuations pop up, but there's a reason for them, and so we are looking into that. We're very interested in really unstable magnetic systems. That's a general area that I've been fascinated by for many years. We're very interested in harnessing localized excitations in these nonlinear systems. How impurities flow, filtration processes work. Remember, I told you about carbon pollution. How do filtration processes work? Not a simple problem. Really tough problem at the borderline of continuum mechanics and discrete mechanics. Granular crystals, they're just made out of grains, but organized as if they are crystalline or semi-crystalline. We are working with some of these systems to literally make sound insulators. You put it around your ear and you hear nothing at all. Okay, turn off your hearing, at least to the ear. And guess what? Partisan political processes. We have been doing some model with random field Ising model. And actually in collaboration with some colleagues in political science at UB for now, on how to model ongoing partisan political processes like elections or election campaigns or what have you. Not only that, but we can also fundamentally ask the question as to how can you change the system so it works better, if there is a better way of working at it. So I'll close here. I'll not speak anymore. I'll stop here and I'll let you think about what I said. And if you have any questions, I'd be more than happy to talk to you about it.
So I mean, I'll get the questions rolling. You mentioned that you're working primarily, with these non-integrable systems using statistical mechanics. What tools in your toolbox, generally are you using to get this accomplished? Right, average day. You're running numerical analyses? I'm guessing simulations and such.
Yeah. So that's a very good question, and thank you for it. Look, there is only one thing that we can solve really well, and that's the harmonic equations of motion, right? You know that by now. So if you don't know what to do with nonlinear stuff, that's normal, but that's also very exciting. So question is this, how do you solve it? And literally, your toolkit runs dry very quickly, which also is a tremendous opportunity because we are fortunate to live at a time where you can actually do very high precision simulation, and then make sure that your simulations are good uh, by conservation laws and so on. So the way I have kind of operated in this space quite successfully is by doing a two-step process. First, we do simulations and try to do them really well, better than anybody in the world almost. And then once we know the simulation results, we try to develop at least a good phenomenological explanation for why we see what we see, which forms the basis for the third step of whether you can actually address them theoretically. I have not been able to take the third step in too many problems, but there are problems where we have taken the third step. Notably, for example, a 2001 paper I wrote with my then PhD student, Marian Manciu, where we proposed a solution for an essentially impenetrable nonlinear dynamical equation for granular systems. The solution stands to, even to this day, as a unique solution that was proposed because our solution was recovering numerical results. In 2018, we wrote a paper with a former student, Alexander Wesley, where we showed that the Fermi-Pascal problem, which is an unsolvable problem so far, you can solve it using our proposed corrected or improved solution of the 2001 solution, which I think is remarkable. Not too many have caught on to it yet, because these calculations are not just plain analytic. You propose a result that is based upon what you think is happening and why it's justified. And then you got to move them forward numerically, because analytically moving them forward almost becomes nonsensical when you start generating thousands of terms in every step. So that's one way. Some problems are simply not doable. For example, if I'm to understand how a micron-sized particle is going to move through flowing air, right? This problem is really not doable with equations of motion because it's so complicated. As it goes up, pressure changes, right? There is differential velocity. There are buoyant forces that come in. There is gravity and the wind frequency, right? So if you were to paint a picture, then you begin to see how many things have to come in to describe this. So you don't model it with equations of motion. You can model it as essentially as a hopping problem on a 2D lattice at the simplest level, and as a hopping problem on a 3D lattice of a particle. And the science of that is very well developed. You can do it numerically. You can even do it analytically. Okay. So can this problem be solved? I'd venture to guess probably, right? Has it been attacked? The answer is no. Why not? I don't know, right? Yeah. So part of the problem is that's why I spoke about curiosity. We are not curious enough. We get stuck in the bloody silos where we exist. And you can't be a scientist in a silo. You'll be a pretty lousy scientist, I think. At least in the domain of having bigger impact. If you want to solve one equation, that's the goal of your life, by all means. Silo is the right place. And so many of people I respect so well do that and do that so well. So there is room and space for them. That doesn't satisfy my intellect somehow. I grew up in the third world. I know the third world problems. I know how they look like. And if I forget that and just do physics, I'm not being honest with myself. And I think for all of us, there are similar strains because we all have a history, as I said. And it's very important to wrap it around in our lives. I have more than answered your question.
Yeah, certainly.
Any other questions?